Okay, welcome to Chapter 6, Finite Difference Methods. In this chapter, we will talk about the so-called finite difference methods, and these are techniques to solve basically partial differential equations. So here's a brief motivation. Partial differential equations, or the so-called PDEs, are widely used for option pricing purposes, and we will mainly talk about the Black-Scholes partial differential equation in this chapter, and we will see how we can solve this problem numerically. And Black-Scholes PD is also very closely connected to the heat equation problem, which is well studied in physics. And basically, PD approach is quite powerful for especially pricing different types of financial derivatives, except the high-dimensional problems. If we have high-dimensional problems, or if we have some more complex payoff functions, then actually Monte Carlo method, which again we will cover, is going to be our main method. So let's see the Black-Scholes model. So in the Black-Scholes PDE, basically the dynamics of a financial derivative, denoted here with this F term, is described with this equation. So this is coming from the no arbitrage arguments in the Black-Scholes model. So, however, in our course, we don't discuss the derivation of this PDE. Just the partial differential equation is not enough to solve it. We also need to have some initial or terminal condition depending on the problem. And we also need the boundary conditions. So a generic first order linear PDE can be written as in equation 2. You can see that the highest order derivative terms are just the first order partial derivatives, and you can see that we have these coefficients which are given functions of the variables x and y. So we don't have any nonlinear terms in terms of the f, and basically this is just a generic form. And you can extend this to a second order representation by considering possible second order partial derivatives. Since here we have just x and y, so you can see we have the second order derivatives in terms of x, or potentially we can have cross differentiation with respect to x and y. And you also might have some first order derivatives as well. So next we will actually consider more specific financial derivatives, which is actually the European call option to start with. And because under the European call option, we can define our actually terminal condition, and we can also consider our boundary conditions, as you can see. So here, since we know the payoff of the European call option at the terminal time, so this is actually a terminal condition here. And the boundaries, since the stock price can take values from, let's say, 0 to infinity as our boundary, so we need to specify what happens if the stock price goes to 0, or what happens if the stock price goes to infinity. So these are the two boundaries that we should consider in the European call option pricing problem. And you can see that since this is a call option, if the stock price goes to 0, this is what you will have because of our payoff. And if the stock price is going to infinity, then you can consider that the call option payoff is approximately just S. So basically, we will also set up the connection of this problem with the heat equation as our next step.